to leave the meeting room, and we will also need to turn off recording of the Zoom call, because then the committee is gonna discuss, and at the end of that discussion we're gonna call Billy back into the room and sort of give him a high-level feedback, although typically the committee will share written recommendations with Billy. Any questions?
I'm good. Yes, thank you.
All right, so thank you, everyone. It's 10 minutes past 3, so probably Billy present until about 3:55.
Yeah, that's the plan. Yes.
Great, thank you.
Should I start?
Yes.
Cool. Yeah, thanks everyone for coming, and thank you for everyone on Zoom to joining as well. I'm excited to have you here. So today I'm going to, talk about what I've done in my PhD and propose the thesis. So my topic is towards robust audiovisual learning. As we all know, audiovisual learning machine learning has been applied into many smart devices, including smart speakers, smart cameras, content filtering algorithm in large social media companies. These are all safety critical tasks. So now do we need to understand its robustness, accuracy, but also robustness as a key factor. On the left side, we see, as the field is progressing, transformers are beating CNNs in terms of a performance, not only in vision, but also in audio these days. And we still have to worry about noise. Noise in terms of both natural noise and adversarial noise. We've definitely seen that adversarial noise like that can fool a classifier, image classifier, from recognizing giant panda to caption. And then still, whether CNNs are more robust or transformers are robust is still up in the air, and it's pretty complicated. So I'm gonna try to solve these two questions in my thesis. One is how to build an audio only or audiovisual system that performs well. The other is how to make them robust to noise and adversarial perturbations. So I'm going to break down my talk into 4 parts. First, let's verify the bad guy actually exists in the real world. By verifying the threat actually exists in vision and audio. This in part 1, I'm going to show you. Let's take a step back, and I'm going to show you how people build the best performing large-scale audiovisual systems, both from the CNN family angle and the transformer family angle. Third, part 2, I'm actually going to expand onto the more multimodal settings and then analyze using adversarial perturbation to see what are the main costs of robustness, and then how can we build a system that is robust. And then we will go to proposed work, which is the work that I have left over to be done. So let's see, what are the actual threats in real life vision and real life audio? So let's first see what is an adversarial example. Normally, how we train neural network models are by minimizing the loss function of basically the loss function is the amount of error that we quantify we want to minimize this loss function so that the neural network can make least amount of error. But when we're training adversarial perturbations, we are playing as a bad guy. So we are trying to leverage the delta, which is feeded together with the input, and then we maximize the loss function, and then to find out which delta is actually doing most damage to the loss function by reversing the direction of the optimization, so that we can find the adversarial perturbation that does the most damage to the original loss function, so that we can have a strong attack. So we've seen attacks like this that modifies stop sign, or making a classifier that misclassifies a turtle into a rifle, and then even people can wear an adversarial t-shirt to dodge the object detector to basically get into the stealth mode. But these are actually not that scary yet, because they all require illegal activities by tempering the object of interest. What if we can not modify the object of interest, but perturbing the light path or the perception pathway. So in this case, here's an example we've done in 2019. We printed a piece of a transparent sticker using and then put several colored dots on it. That dots will fool the image classifier into believing that a stop sign is actually a guitar pick. So how do we do that? So following the same principle as we talked about. By the way, the algorithm is called projected gradient descent. The projection is basically the allowable set of parameters that we're allowed to operate in. So in this case, what we did is we mimicked the light path of the entire perception of the camera, and then try to tune the few set of parameters, including the color of the dot, position of the dot, and also the alpha blending. The alpha blending is the algorithm or the computer vision algorithm that mimics how light will strikes on a piece of a dot and then results in a blur. So basically, we try to mimic or simulate the blur in order to simulate however the light travels through the camera. And by maximizing the parameter of those sets of the dot parameters, then we can maximize the attack effect of our the effect of our attack and make the classifier misclassify. So here's how it works in practice. Basically, we first, for example, we print out a red dot, and we're trying to use a similarity loss to measure how the red dots result on a camera CCD and what does the camera see. So basically, once we get a set of parameters that we can actually create a fidelity simulation of the blur resulting on the screen, then we would be able to plug all these parameters back into the projected gradient descent algorithm and be able to basically plug in and optimize those sets of parameters to maximize our target loss, which is the rest, which is the loss, in this case, the rest net loss, to reverse the direction and maximize it, and we can create a tag. And this is how we print it out. It's quite fun. So, and how it's working in action, basically, you can see, stick that on, the camera will, the ResNet model deployed on the camera will be misclassifying a street sign into a guitar pick. So similar concept can be applied directly onto audio. So we were, these threads are real in vision. So we're showing an example in audio, same way. So we know that a simple classifier in audio is the wake word classifier. So and a lot of smart assistants such as Alexa or Siri use this wake word detector to wake up. But what if there is a music playing while your wake word might have trouble waking up? So we're trying to craft that piece of music that's playing, but while that music is playing, then your wake word will never be waking up. And there are two more challenges compared to vision if we're operating in the audio domain. First is that we do not have a white box gradient to the model anymore. And then in actual audio domain, there is a thing called room impulse response. I'm sure a lot of you are expert about audio. So there are also environment noise existing in the room, so that interferes with the adversarial perturbation that we are computing. So how do we solve that? So we use gray box assumption to bypass the black box barrier. So basically what we did is we reverse engineered a lot of papers from Amazon Alexa's group. In this case, we mimic their architecture. The key assumption here is that if our emulated model's detection error rate is in the same ballpark or in the same order of magnitude, then our assumption is that the gradient of our model should resemble the gradient of the real Alexa model. And thus, the attack that work against our model should have transferability towards the real Alexa model. And how do we tackle room impulse? We plug all these things into the loss function, which we're going to cover later. But what are we generating? What is the adversarial perturbation itself? It's we use a piece of guitar music in this case, and we use a physical music synthesizer, which is Karplus strung synthesizer in our case. All we need from this synthesizer is a set of parameters that we can differentiate through and then we can, all that we need is optimize these sets of parameter that plug back into the projected gradient descent. Namely, in this case, is the duration of the key, the note of the key, and the volume of the key. So basically, we're playing a set of guitar notes, and then this piece of guitar music is supposedly able to fool the Amazon Alexa into not waking up. So how do we plug the room impulse response and the psychoacoustic effect into the loss function is shown as below. Basically, we take the room impulse response as a transformation, wrap it around with the input function, and also we include the psychoacoustic effect as an additional loss term to optimize, so that we can create a piece of guitar music that's able to fool the real Alexa in the real world over the air testing in various angles with different volume settings and then various distance settings. So basically, this table shows you that it works. Our simulated model will operate at about over 90% F1 score when it's clean. But with the adversarial perturbation, in this case, the adversarial music, everything is brought down to about only 10%. So it's very effective in a real world. We have demo videos on YouTube as well. So now that we know threat exists in both vision and audio, so let's take a step back and let's revisit how do people train audiovisual models in reality. And mostly in part one, we're going to cover how do people build audio models. And then, so there are CNN and then transformer family. Let's dive into CNN first. So CNNs are kind of de facto models that everyone use, especially in ESPNet. There are a lot of CNN models as well. So back in 2017, we did a comparison of CNN versus all the other neural network models. CNN just shows very good performance. Basically, it's better than traditional models like Gaussian mixture models or iVector, and it's also very competitive against the DNN and RNNs in a log-mel filter, using log-mel filter as features. So what is CNN actually doing, or like what is the caveat of building a strong performing CNN? So let's take a 1D CNN, for example. So first question is, the deeper the CNN, the better. We found out in 2017 that is not the case, or it is the case, but it's complicated because it is in general the case that the deeper the CNN that you train, the better the performance you will get. But there is a catch. In our example, if you go to 34 layers, the CNN will actually overfit. So it's not an infinity, basically. But the side benefit of using a deep CNN is that the training time in this case, you can see, does not linearly grow with the network depth. That's due to the checkpointing behavior in the neural network libraries they implement. So you get a free benefits of training a deep CNNs, and that's same in audio task as well. And then what are the tricks of training deeper CNNs? Batch normalization is a key, and also do not use fully connected layers versus fully convolutional layers. Fully connected layers only add to the number of parameters, but they do not add any marginal gains to the actual performance. So what are CNNs actually doing? We all know that CNN is basically a kernel that is striding through the entire input matrices in a one-dimensional case. What is actually learning? So this shows you what is actually learning. In the first layer of the CNN, one-dimensional CNN, if we actually do FFT again on its weight, you will see things like this. This mimics the filter band that we design in traditional signal processing. And the interesting thing is that the number of the size of the filter itself largely determines what it learns. So in this case, you will see that if we have the filter size too large, it will tend to learn fine-grained filter banks. But in the high frequency, it's chopped off, so it's missing the high frequency component. But if the filter size is too low, then it will learn a dispersed filter band. So it's not going to be seeing very clearly. Only the filter size, which makes sense in the audio case, which correspond to the 10 milliseconds interval, which is it's kind of proven in a, not proven, empirically proven in a signal processing world that what ear correspond to, that has semantical meaning, that performs the best. Also, you will see the filter banks actually is the most consistent and covers all the frequency bands. So this is in general what CNN is doing on audio. So all the previous tests were done on supervised tasks on a relatively smaller data set. So in 2017, Dan is the main author of Google Audio Set. So I will definitely, that's a huge development in the audio field. Basically, they collected millions of videos that contains 500 different, over 500 different audio classes to basically serve as a benchmark for the audio community versus the ImageNet. So it's equivalent to ImageNet in the audio domain. So the first question is, basically now we're operating, we have the YouTube video, we have more data. Does adding a visual modality or does adding visual cue help with our audio recognition? The answer is actually a little bit of complicated. So in general, overall, in certain subset, you can have some marginal performance gain, but there are classes, there are counterexamples that will adding a visual cue will actually hurt the performance. In this case, for example, police car, ambulance, and then fire trucks, they tend to co-appear in an emergency event. So adding visual cue, because the visual cue will see three things appear together, but the audio will be able to identify each individual things. So it actually hurts the performance of these classes. So take a grain of salt of someone telling you that adding visual cue always help with an audio performance. And the other challenge brought by audio set is that the label it offers is weak label. What do we mean by weak label? We don't know when the events happen or when the events start or end. We only know it exists in that 10 seconds, for example. So how do we tackle this? We tackle this in a neural network setting by leveraging pooling functions. So the idea is to use the precious bag level label only once by aggregating the frame level predictions to compare with the bag level predictions. This is only achievable through using pooling functions. You will have a frame level predictions, say 10 seconds each, and then you have 10 predictions, but the pooling layer will take care of the aggregation. So in this setting, it's a very typical settings for multiple instance learning. And then in 2019, we did a comparison on, so what is the best pooling function in this case? We compare max pooling, average pooling, linear softmax, the normal exponential softmax, and the attention pooling. And you can see it actually doesn't differ much. Only the linear softmax shows a little bit better performance in terms of localizing the sound. So it's not a lot. And that is the state of art that time. So now we have a hang of we have a taste of what CNN does in audio. We move on to transformer families. And then that's where the literature gets explosion after 2017, after we see transformers taking over in NLP or vision task. So the first thing we did is we re-implement everything and we put everything into an apple-to-apple comparison and open source the code. I think I still believe that open sourcing and sharing our implementation, documenting our experiment is the best way to sort of give people an intuition. Why do we do that? This is overview. It looks chaotic. This is actually what is happening in the field. You can see everyone is using different number of parameterized model. Everyone is using different optimization tricks, and a lot of people reported on the different subset of audio set with a slight modification of numbers. So it's really hard to have an idea of what kind of models or what is the best practice of building the best models. And especially with transformers here, so there are a lot of, say, tiny details that matters in modern training techniques of transformers. So let's first revisit what is pure transformer settings in audio. So how do we use it? This is all inspired by the vision transformer in audio. It's actually very similar to vision transformer, where we actually stride through the log-mel spectrum in this case. So treating the log-mel spectrum as a piece of an image and then striding it in both temporal and frequency domain. And then we can say like one chop of say one patch of a 16 by 16 patch is worth of a word, audio word, basically. That's how we did in pure transformer settings in vision, in audio. So kind of an empirical sort of a table show here that you can see using a 64 by 400 dimension feature or using a larger feature, the number of patch will also grow quadratically if you diminish your, if you decrease your striding size, and then so does the training time. So there's a trade-off of roughly O of n squared. Basically, that's a well-known fact of self-attention and then the transformer mechanism. So, but the better performance will show up once you stride more carefully. But the problem with that is that you can see when you use larger features, it will not fit into a commercial GPU anymore at certain points. So you cannot go infinite with using vision transformer architectures. Now that we put everything back into comparison, let's compare pure CNN, pure transformer, and in between there are lots of hybrid architectures. And how does each individual module different with each other? So here's what we did. Basically, we put them into a fair and a square comparison by comparing only the non-ensemble model without any, with only single checkpoint models without any multi-model mix-up. So basically, you can see here, transformer models do perform very well, but the problem of that is that they are actually surpassed by CNN transformer models. So, and then the number of parameters for pure transformer models is huge. So that's actually showing that transformer might not be the best candidates for building an audio or visual recognition models. And this table is so far, I think, the most fair comparison that we have done to show that how does everything perform on the same sort of a scale. And so the second major question we want to answer is that what about all these modern training techniques? Are pre-training actually necessary? What about all the other tricks? So I think we've done a lot of studies, and then we will cover in, we can go offline talking about the details, but the most important things I want to talk about here is the pre-training. What pre-training is actually doing in a transformer setting is actually warming the models up for only so it's most effective, or it's most prominent in the heavily parameterized models. As you can see, VIT here contains the most number of parameters. So without pre-train, the model simply would not be able to perform well. So it will get stuck in a relatively low performing region, and then it will never do well. Whereas if the model itself doesn't have a lot of parameters, then we don't really need any pre-training to bring the model to a high performing region. So you can see the models that initialized with random start can eventually catch up to those are pre-trained later on. So it kind of tells us that pre-training is actually not always necessary for all the models. Only the models that are heavily parameterized relies on pre-training to warm start. So all the other optimization tricks, including learning rate, scheduling batch size, and whatever gradient accumulations, they're less important, but learning rate and batch size seems to be the most important among them all. So you will see basically, if you start at a wrong learning rate, the model will get stuck. Also, too large of a stack will also make it a traverse into the wrong parameter region. So basically, you want to tune learning rate linearly. So there's a paper in called don't decay the learning rate, but increase the batch size. Basically, following that intuition should be able to train a large transformer model pretty smoothly. And another sort of a side effect of a large evaluation on large scale data set is that there are actually quality differences in the audio set labels, which means that the label contains a lot of noise. And then if you only evaluate on the lower quality samples, that the model will suffer more. So if you evaluate on the only high quality, so quality means that the event tag there are actually existent in a real data set. So basically, there are sort of a special attention you need to pay on the data itself to report a score. So the last fact about reporting or building a high-performing model is basically data augmentation, and then how much does that affect our model? You can see here that normal like or usual augmentation tricks like spec augmentation, mix-up, or data balancing, they affect about 2 to 4% difference in bringing up the model performance. But in our finding, we find out like different type of normalization tricks, they affect the most. They affect about 10% of the accuracy, which is significant. So we have to pay special attention how we normalize the data itself. So that's about everything that in a supervised realm. So in 2022, as a self-supervised is taking its popularity, so we want to explore if self-supervision can actually help with audio tasks as well. So especially in a transformer setting. So we took the idea of a masked autoencoder and used the reconstruction as a pretext task. So basically what we're doing is we use a masked autoencoder to reconstruct the original log-mel spectrum, and then we plug them into the encoder and decoder framework, as we are very familiar with, and then we explore different type of masking strategy by not only striding, but also doing random masking, but also expanding the windows. And then we eventually found out that we can not only beat the supervised baselines, but also there's a special type of transformer that called a swing transformer that's also incorporating the intuition of a convolution back in. So that's the best performing model that we're using. So basically, we're seeing here that the best performing model is also a hybrid model here. So here are the kind of overall takeaways for how to build an audio and visual system that, or audio mostly, to the highest performance. So there are several caveats. Basically, we found out that pre-training is not always necessary, and then modern training techniques like learning rate, decays, or batch size pay special attention to these factors when we're training large models. And the trade-off between transformer and then CNNs are still very severe. Like transformers are heavy models, and then they're harder to train, and they actually rely more on the positional embedding because the spectrograms are translational variant, not like images. So and then in the future, we do find the self-supervision is very promising, and then they tend to scale better to unlabeled data set. And in our experiment, everything is pointing towards models that with local and global features. They are the models shows the most promising future so far. So I think the perception is merging. So now that we know how to build a high-performing model, so let's focus on robustness. What do we mean by robustness actually? So we've seen robustness is getting overloaded, or this term is overloaded in many different contexts. In Wikipedia, robustness definition is the degree to which a system or component can function correctly in the presence of invalid or stressful environment conditions. So adversarial robustness, as you can see in this Venn diagram. This Venn diagram is a kind of a derivation that I excerpt from different books, theoretical books and everything. So it shows you adversarial robustness is the worst case scenario. And normally what we talk about robustness, it's indicating input robustness. For example, if you have an audio system and if you have perturbations or noise in the audio system, what if you bring in another modality that can help you to counter the change in an audio input? We're not worrying about parameter robustness. This is what we did in other works, which is kind of a noise that you introduce by quantizing the weights. So these are different type of robustness when we're evaluating a machine learning model. So here are the paths towards understanding how do we build a system that is actually robust. So in 2018, we did a kind of a surface level study on what is the best way to tackle the input robustness problem. And we use the vision to text, video to text, or retrieval task as our studying ground. So specifically, we worked on a MSR VTT dataset and an MS video description dataset. So basically, the task is to retrieve a text from the video, vice versa. So here are a few challenges or the problems. It's obvious, right? So we have a vision backbone, we have a textual backbone, and how do we fuse them together? And we have an audio backbone. What is the best fusion techniques? Whether it's concatenating, or should we project them, the latent vectors, into the same common vector space, or should we project them into multiple subspaces? So in our study, we found out that projecting them into different subspaces results in the best empirical result. So specifically, what we did was projecting the audio and the motion vision, like audio and motion vision features into the so-called activity text space, and the static vision and the text features into the object text space. Doing this, so there are three benefits of doing this. So first is actually it's more robust to distribution shift in individual backbones, or in individual vector spaces. And then doing this actually make us capture the contextual information between the moving features and the text, and the static features between the text better. So there are more grounding capabilities of those projections into the different vector subspaces, and it suffers less from a curse of dimensionality, because we're not trying to project everything into the same huge vector space. So doing this is actually more beneficial. The other thing to worry about when we are fusing different modalities together is the loss function. How do we design the best loss function that is most suitable for fusing different modalities? Usually, people use a so-called notion of a pairwise ranking loss, where basically when you have a video and an audio input, you want to retrieve the pair, but there are positive matching and a negative matching. So in a vanilla pairwise loss, basically we're aggregating all the positive pairs together with the negative pairs. So basically by taking everything together, where the modified in 2017, the advanced version of doing that is taking the idea of a hard negative. So hard negative means it is almost a positive matching, but it's on the verge. It's still negative. So they're taking the max of the negative matching. But we found out both things might not be ideal. So we did some modification there, and we proposed the idea of based on semi-hard negative mining. So we did a weighted average of these things, and then show that our loss function is actually better off. So this is the performance on the MSR VTT dataset, showing that the blue arrow shows that our loss function is indeed better than the vanilla loss functions. And we also see that we talked about the fusion different fusion techniques that we mentioned. Doing projection into multiple subspaces end up being better than concatenation or projection into the same vector space. And they're way better off than unimodal models. So it shows us, give us a take on how does a different fusion actually, what is the best way to fuse different modalities. And here to note that how vision VTT is evaluated is through recall at 1 to 10 and ranking, the median ranking. So ranking is the lower the better, and recall is the higher the better. And our system are shown to be better off than other baseline system in both recall and ranking. They're basically surpassing the previous baselines. So now that we know, we kind of get a taste of input robustness. Let's actually take us, so in 2022, we looked at where we have looked before, and because the advent of a so-called notion of contrastive learning, so we updated ours. We did another try, and we're still perfecting it. So we built a system that is using contrastive learning, and we are ranked on third place in terms of CIDR score in a TrackVid VTT challenge. So it's the same challenge. We're reusing the same ideas, but using a different type of formulation. So these are a little bit of a qualitative samples. It shows you that in 2022, the system is able to pay more attention to color and specific activity details, especially in a different modality. So that's how that's how we understand input robustness. So let's take a step back. So and then how could we, like, basically what we have done is still trying to empirically see the results and then trying to make the hypothesis and empirically test our hypothesis by seeing the downstream performance. Can we take a step back and then take a reversed approach to understand a certain model by using adversarial noise as a scalpel to break it? So once we break certain things, then we can use that as an ablation and trying to interpret what is actually going on there. So simple thing, we talked about different fusions. What are the differences between these different fusions in terms of robustness? We can fuse the model from early fusion to late fusion all the way in different places. Which one is the best performing in terms of being influenced under the influence of adversarial perturbation? This is where the difference advent. So you can see that late fusion are clearly more evident to be more robust to adversarial perturbation. So what about the different frequency band in a log mile spectrum? Which part influence the end robustness the most? We will also see the different. We're seeing a difference here, right? So basically, the lower frequency tend to be dropping less than. So if we're adding the adversarial perturbation onto the different frequency band, we'll see that the lower perturbation, adding perturbation onto the lower frequency band results in more of a performance drop. That indicates that the lower frequency bands are more important for robustness of audio classification models. Whereas if we slide or compute the adversarial perturbation at the different temporal mask, that does not differ too much. So showing that by masking off different temporal domains of the audio, the entire model does not tend to differ that much. Basically shows you that in a spectrogram, only the frequency bands difference are more crucial to the robustness difference. So what about all the architecture differences? ResNet seems to be a little better than all the other models in terms of robustness against the adversarial perturbation. But in general, we don't see a huge difference between the clean performance and the performance under the adversarial perturbation. So basically here, all the setting, you can see a pattern here is a clean versus perturbed performance. So you can tell that how much the performance drop, then it indicates how robust the model is. So taking a closer look, you will see we want to see like whether different classes actually differ in terms of robustness against the same perturbation. The most robustness classes, for example, here you can see the red box, music and speech, they are very robust. But why? Because one is that they are trained on a huge number of samples. Only music and speech alone accounts for like 80% of training samples of an audio set. So those classes are very robust. And all the other classes that are robust tend to be smoke detector, ambulance, police car, or heart sounds. What they're sharing in common is the structure of the sound. They're actually consistent. All of these classes tend to have a set structure in their sound features. So they are actually benefiting from that in terms of robustness. And what are the things that hurt robustness? For example, whale sound that is way later showing this bar chart because it's sorted. So whale sound or all those high frequency audios, none of them is robust. So is there a way to quantify these things? This is what we're going to talk about in the next section. So we kind of take a step back and revisit how people quantify robustness in the field, there are people trying to, so folks are trying to leverage convex programming to derive a bound to quantify robustness. But doing that is basically bringing the nonlinear neural network back into the convex land by doing either convex relaxation or simply making the assumption that all the neural nets that we're using is linear. But those things are shown to be not very realistic, or the bound they derived are too loose. And the killer point is that all these convex theory-driven approaches are computationally very expensive because they're all beyond the land of quadratic programming. So they involve a huge cost when doing it on the large data set setting, which is not realizable. The only workable solution in reality is called adversarial training, which is by adding the adversarial examples that we talked about back into the training and train another model that are aware of the adversarial examples. And then only doing that will show protections against the adversarial perturbations. But doing that also involves huge cost, and the clean performance of adversarially trained models is actually dropping quite a lot. So is there a way to fix that? So here's motivated by all these above factors. So we're trying to answer a few questions. First is, are doing multimodal actually better than unimodal at all? And we found out not necessarily. So taking a closer look of the multimodal fusion setup, we are finding that the multimodality of input of adversarial perturbation actually allows for more parameter space. So basically, intuitively, multimodal models allows a larger set of parameters to be exploited by the same adversarial perturbation. So it will actually allow the attacker to have more budget attacking a multimodal setting if they have access to both modalities parameters. So a simple theoretical, we showed that in our 2022 paper that a simple theoretical example and an intuitive explanation is that, in a tiny nudge in the audio embedding and the video embedding will translate into a drastically different nudge in the audiovisual embedding space. And this nudge will most likely to be out of the boundary of an original decision boundary. So the common assumption that we hold for multimodal models tend to be more robust and unimodal models are not true. So we take a best study, like, because we believe in those hybrid models. So we bring one of those convolutional and transformer networks into study here in a multimodal settings. So we take that as an example to study that. Then knowing all of these, can we quantify them in a different manner, or what is the promising way of quantifying them, and thus using those quantification to inform us to design a better mechanism for fusion or training a model that is more robust? So let's first talk about how to quantify them, which is design a metric that is quantifying, but not by the convex programming, but by the class-wise metric, robustness metric. So basically, we design a metric that is inspired by density of a high-dimensional ball and then convexity. So convexity in the neural network setting is that we all know what is convexity in a classical setting. In a neural network setting is basically, let's connect the two dots in an embedding space and take the middle point of the two dots and then see if that middle point is prediction is still in the same decision boundary as the original classifier. So if it is in, then we call it convex. If it's not, then it's not convex. So the density and convexity are the metrics that are the inspirations that we taken to design our metrics. So the more details can be viewed in our paper, but in short, we show that the metric that we design as a convexity and the density tend to have display a linear correlation with the adversarial robustness. So using this metric, we can actually have a pretty good estimation of how a class is in terms of a robustness. So for example, if the class is denser, then it's more robust. If the class is more convex, it's more robust. For example, here, emergency vehicle siren or civil defense siren tend to be more convex and denser, and they show the better robustness overall. So we observe that in general, linear trend of these correlations. And how can we use this quantification to design a better mechanism to fuse everything together, to design a better training mechanism for building a robust classifier? So that's through a simple trick is through mix-up. Basically, we want to only select those denser examples and the more convex examples to train on. So basically, through the mix-up process, we want to only train on those more convex and then denser classes, and hoping that our trained classifier will result in building a more robust model. And then in our experiment, we demonstrate, we show that it is actually this case. So with our convexity and the density aware mix-up, we can train a classifier that is better than, not only better than the vanilla mix-up fusion, but also better than an adversarial training with 2.1 speed gain. So basically, adversarial training achieved the same same degree of protection, but they are costing way more than our proposed mix-up. So we show that in general, that multimodal models are not necessarily more robust, and then empirically, later fusions are better than earlier fusions, and models trained with more data are more robust, and data with more structure tend to be more robust. And there's a huge promising direction that we can explore by quantifying robustness and design training mechanisms accordingly to design a future cheaper way of achieving training more robust models. So yeah, that's everything about my work that's done. So there are a few things that are left in our previous sections. So apparently you see that we've touched up on self-supervised learning, but we haven't done a thorough study on this, whether self-supervised learning through other methods, such as Dino or Moco or other pretext tasks are better or worse are not known. So we can also study their robustness differences. This is I believe, an interesting thing to explore in the future. And thus, I would say in the next few months, I would like to do a comparison of the non-contrastive approaches of self-supervised learning with the contrastive approaches, and systematically compare and then understand what are the differences between these things, and what are the representations each self-supervision techniques are learning. Do they actually have a difference or not? So this is one thing that we want to I want to work on in the next few months. And the other thing is that we've talked about adversarial robustness, and there's in a more traditional signal processing definition, there's the robustness to noise in general. So we want to study, we haven't really answered whether adversarial noise directly translate to better robustness against the noise. So we want to compare whether these things are actually correlated or one leads to another. So, and then there's a notion of flatness or sharpness of the model. So we want to see whether these new metrics could be helpful to interpret the robustness as well. Basically, what we see as an interesting in the future is to do a thorough study on all these metrics that can quantify robustness or adversarial robustness, and then kind of build a liaison or understanding between all these properties of neural nets, and then tell people a consistent story of whether one type of property would lead to another, whether robustness will be, whether flatter models are more robust, for example, or whether the more adversarially robust model will necessarily fend off natural noise in a real world as well. So the last aspect is, as we talked about, I think contrastive learning is a promising field for starting from 2020s. So that's apparently what we're missing. We only done a preliminary study on contrastive learning. So, and then in talking about contrastive learning, there's the model called the CLIP, as everybody knows, and CLIP can do a lot of different things. So I would say in the next few months, I would like to do a thorough study on contrastive learning and explore whether using CLIP type of a contrastive learning, whether we can build a better fusion of all these different modalities. So that concludes most of my work and my plans going forward. Thank you everyone for attention. It is a lot of stuff, so I hope I give you a glimpse of the high-level ideas, and yeah, please let me know if you have any questions in a Q&A session, and thank you for your attention.
All right, thank you, everyone. So usually we start questions with the external committee members, and then go to the internal members. So then you would be first, I guess, followed then by Emma and Shinji, and then me, before we open it to the general public, the room. You want to do that, Dan?
Sure. Okay, thanks a lot, Billy. It was a very nice set of work, and I think that I like the way that you have this brand of doing these very thorough investigations and really trying to go back and give definitive answers to these things which people have kind of sketched around. I think that's very nice. Talking about this stuff with the trying to figure out just what works best in straight up audio set classification. We did some work recently, which we've just submitted to ICASP, on trying to examine the benefit balancing, because of training set, training batch balancing, class balancing in training batches. We couldn't reproduce the published results in our own system. And what we found was like things that worked on the external eval set didn't work on our internal eval set, which had a slightly different composition and mix of priors. The question that raises with me is, how significant are these changes that we're talking about? So we're talking about, a few, hundredths of a few percent in MAP, and people can make statistically significant changes in this. But it turns out if you change the eval set, you get different results, contradictory results. And so I'm concerned that actually all these numbers we're talking about are kind of within some kind of margin of error for these systems. And I don't really know how to think about that. I mean, I know we have this one way of thinking about it, which is we've got the second eval set, and we can see if the results carry across, and they don't. So I'm wondering, like, what do you think about the how to decide whether we're just playing around in the noise versus actually making significant changes, improvements to the techniques for classification?
Yeah, that's a great question. So I think we're referring to the slides that I mentioned here. So in this slide, to reiterate, what I was saying is that if we evaluated the model on different quantile of the data set according to different quality quantile. So here, like basically, if we're evaluating on everything, then we only get 40%. If we only evaluate on the highest quality data set, then we can get 50% MAP. This is huge. So I wouldn't say everything is in the noise, but maybe I would say, I would propose that if we do different runs and then add the error margin there, that might be indicative of the model's performance overall, rather than just reporting MAP or D prime. So I would say even introduced the notion of a calibrated error in terms of a measuring basically introducing the idea of a calibration, neural network calibration into this as well, and report the ECE instead of just the MAP. So I think yeah, this is definitely a huge question of evaluation on huge data set. Even in ImageNet, there are people trying to say that are bad examples from ImageNet, the raw differences of a 2%. What does that translate to the actual model performance? Are they really learning the right thing or not? So I would say going into the future, we have to be more careful evaluating on audio set as well. Maybe we should provide more interpretations of the model and also report overall performance on average on different runs, and then report its error margin as well. Does that answer your question, Dan?
I mean, I don't know there is a good answer, but yeah, I think we're agreed about the problems. I think one of the big problems is that we've got a public evaluation set, and so it's very difficult to avoid people optimizing. Whatever single measure you come up with, people will keep making changes that will necessarily be favored by the evaluation set, because that's all you've got to follow. But we can't tell the difference between things that are actually truly generalizing and things that are just optimizing for the particular evaluation set we're using. But there's no short of having a hidden eval set, a la NIST evaluations, then there's no way around that.
Yeah, I concur. So I mean, I think along the other line, what I would say would be promising is to encourage the community to report on downstream task as a zero-shot transferred, like a transfer performance as well, so that we can have a fair view of each individually trained models, their ability to transfer to other zero-shot data set, whether that being a different domain or like encourage the model to operate in a more like say adverse environment and see whether that model is actually able to generalize better. So I think we could make effort in a community to advocate for people to do things like glue in NLP, but make a kind of a glue equivalent in audio set as well.
Sounds great. Okay, can I just ask you about the adversarial work in audio? So the metric was like you have a single set of adversarial attacks, and
yes.
Then for different models you see how much they can disrupt the classification.
Exactly.
How do you come up with that set of that original set of adversarial attacks? Because ideally an adversarial attack is optimized for a particular classifier. It's the thing you can make it so that it disrupts a particular set of parameters. But then you're moving the model around, but you're holding the adversaries fixed. Shouldn't they get much worse? Shouldn't they be much weaker against any kind of retrained model?
So because we want to use adversarial perturbation as a scaffold to reveal the property of the robustness, right? So we're specifically hinged on the notion of a universal adversarial perturbation, which is universal against all the classes that is trained here. So we measure the average, because MAP is average, is the mean value of the precision. So that is suitable to kind of gauge the model's overall response to the single adversarial perturbation, but that adversarial perturbation is supposed to be universally adversarial to all the classes that is measured here. So measuring, that's our formulation. Basically, we're trying to leverage universal adversarial perturbation as a robustness gauge here.
Do you verify that, for instance, by seeing if the when the net effects vary, are they uniform across all the classes? So it's like, it's late fusion is more robust. Is that dominated by a few classes, or is that uniform across all the classes?
Yeah, we observe the consistent dropping rate, which is not listed here, but if you're interested, I have a lot of tables that indicating the different classes behavior under the same type of adversarial perturbation is a very similar and across different models. So they do transfer well to different settings. So that's why we picked the universal adversarial perturbation as the tool to kind of dissect the model to nullify certain parts and then to understand the entire model's performance better, hopefully.
And so what does this universal adversarial perturbation look like?
So
on the figure, it's saying adding noise. Is it literally just a waveform that gets added, or?
So we did that by adding noise on the model's input. In this case, it's basically log-mel spectrum, right? So it's the same maximizing of the loss formulation. We tune the universal perturbation to maximize the loss in the different locations. In this case, like whether it being high frequency locations or lower frequency locations or different temporal locations. And we found out that this differs quite a bit. It depends on where we add the noise. So it's showing us a universal adversarial perturbation could reveal certain property of the entire model architecture. And the problem of without using, let's say take a counter example of non-universal adversarial perturbation that could be computed on individual samples. So it's really hard to quantify how much of a perturbation we add on to. There's no consistent manner or how to measure. So that doesn't really give us an overall understanding of what is going on in under the hood. So like, let's say we can break a dog sound or break a cat sound, but that attack does not translate into breaking other classes like a truck or a fan. So it's hard to make the argument about the overall performance drop of the model. So that's one of the motivation that we pick universal adversarial perturbation as the studying tool to quantify how much of a performance drop brought by this can we report.
And so just so I understand, this particular attack, I mean, how particular is it? So the classic examples of adversarial stuff, they kind of want to be this very carefully set up, set of small tweaks that will just push the classifier over a boundary. But here we're saying, no, we're not looking for a single case. We're looking for something that's pretty general that messes up things in general. And that to me doesn't sound like, well, you're not going to get a very narrow optimum there, right? It's like something that works really well for one class isn't going to work elsewhere. Something that we wanted to have impact on a bunch of classes, it's going to be pretty general. In fact, it may be like, I'm thinking like it could literally just be a random noise mask with a certain amplitude, and then it doesn't, any random signal will have kind of similar effect. Or is it like, no, it's a particular mask that is actually particularly bad? And how much worse is it than the average case?
Yeah, that's a very interesting direction. So as we shown here, so the mask placed on lower frequency show better or more impact on the overall performance versus mask that is placed on different temporal locations does not, tend to be different at all. And so that indicates that there might be a specific location or so-called sweet spot that we can focus on of crafting that adversarial perturbation to let it be the most damaging one. We don't know what is the most damaging location or the temporal location yet, but in our empirical experience, we show that a frequency band might be a promising direction to look for the most damaging sort of location to explore for placing the adversarial perturbation mask.
Couldn't you learn that mask by gradient descent, like optimize it over a bunch of examples, but now rather than training the mask to, rather than training the weights to get high performance, you're training the mask to get low performance subject to, you know, a magnitude constraint or something.
That is a perfect question. I haven't tried to constrain the shape of mask yet. As we showed earlier, we can try to craft a piece of music that is kind of designing the noise itself, but we haven't really tried to shape the noise itself. We only try to play with the parameters in the noise hyperparameter set. So I would say, yeah, it would be a very interesting direction to explore.
My hope is that there's nothing, because I think the point you make about future work where you want to connect the adversarial robustness to the actual, real world robustness, I think that's really important. And I think that that's not, actually, I think you're pretty close. I suspect that this kind of, this adversarial measure is going to be pretty close to just general classification accuracy. So, but I think that's good news. All right, thanks. That's enough for now. Let someone else have a go.
Thank you.
Thank you, Dan. Emma, maybe next.
Sure. Yeah, so I guess one of my questions is actually sort of a follow-on from one of Dan's questions, but maybe a slightly different perspective. So let's see, I have written down here slide 73 as the one that inspired me to ask this question.
Sure.
Can you, Emma, it's hard for me to understand you. Could you maybe come closer to the microphone or?
Oh, sure, yeah. Sorry.
Thank you.
What is the mic? Is it this?
It's here.
It's your
I think.
laptop?
Yes, I think so. Sorry.
No. Is this better?
This is much better. Thank you.
Okay, no problem. So what I was saying is, I have one question that's sort of a follow-on question, or maybe it's sort of a different perspective, similar to, I think, Dan's first question. And so I thought of it on slide 73, which is like, do you have a sense of how much of a difference? I mean, I don't really work on adversarial robustness, so I don't have a good sense of how to interpret these absolute numbers. And so, you have these arrows indicating that one of these is more robust than the other one, but those like absolute numbers like seem like pretty small differences to me. So do you have a sense of like how much of a difference that would make like in practice in an actual deployed system? Like, under sort of like privacy concerns, or, attack concerns?
That is a very valid question. I would say, because the performance are not like that high, because it's less than 50%, we're doing it right in a clean performance. So I would interpret it in the percentage, performance drop percentage view. So if what I'm trying to show here is the bar in the bar chart, you can see the percentage of drop caused by the adversarial perturbation is quite different in terms of using different protection mechanism. So in our case, what we're showing here that our mix-up, proposed mix-up, is actually achieving a better or longer bar in this case in terms of percentage. There's a visible difference between using a mix-up versus not using a mix-up in this case. So it is showing us that our mix-up is doing something to make the model more robust against the same type of adversarial perturbation after being attacked. Does that make sense?
So what you're saying is the point, I got one point, which is that it's interesting that using mix-up is comparable to basically doing full-on adversarial training.
Yes.
You don't have to do the adversarial training. Right?
Exactly.
It's just like a training. I guess, is that the only takeaway here? So you're trying to say that these are.
So we're showing mix-up, doing our mix-up is better than vanilla mix-up, which is the original mix-up. And
so that's my question number one, is that better, like 0.37 versus 0.33?
That's what we observed. And I would say that 4 points of MAP is a little bit of a difference, or it's quite a sizable robustness gain in my view. Because the percentage wise is translated to about 8%. It's fair to say that. So That's why I also want to show the bar plot. So it's not a whole lot, but I would say this is a sizable gain.
In Billy's defense, that's the size of the, people get very excited about that kind of improvement in that number. But my deep fear is like, maybe we're all, chasing demons.
Yeah. Yeah, I mean, this is like a problem in machine learning generally, right? Not specific to this area. So I had another question about your proposed work. So one of your proposed works involves, measuring sharpness of models, but it wasn't totally clear to me. Like, could you clearly state sort of what your hypothesis is, like what you aim to learn from, about like transformers and CNNs and robustness by measuring sharpness, like given the debate about whether sharpness metrics are useful and how to measure sharpness?
So yeah, I think just to reiterate in a more succinct manner, my question is the flatter the more robust? So we want to quantify that, so we can quantify all the sharpness scores of all these different models and use a SAM, which is sharpness aware minimization, to train all versions of the model to bring them into the same ground of all being sharpness aware. And then do they translate to overall performance robustness improvement of all these models? So basically that will kind of draw a line or finish the debate about whether flatter models are more robust or what architecture actually is the more robust, and then what is the correlation between sharpness and robustness. So this is what I want to do. I mean, the experiment are done halfway. I didn't present any work that is non-published. So in my preliminary observation, we do observe promising conclusion that flatter models tend to be a little bit more robust, but it's also in the MAP difference, as we talked about. If the MAP difference is questionable, then I have to find another metric to measure the absolute robustness differences.
Okay, you don't talk about sharpness aware minimization at all in your proposal, though. Just talk about measuring sharpness. So I agree that if you can actually show, so basically there's like a debate in the community, right? Whether like sharpness metrics measure sharpness, but I think if you were from your proposal, and I think what you said in your talk today, you were talking about just like measuring sharpness using, I think, the definition of like Kaskar et al.
Yeah. I think
but that's different, right, than actually showing like, okay, regardless of like what sharpness actually is measuring, if we do this like sharpness aware minimization, we get better performance. I mean, I buy that that's obviously, like, I've done work in that area. I buy that that's like an interesting thing to show, but that's why I was asking.
Okay, yeah, this is what I actually want to do. So maybe it's not written down here. I thought SAM is inspiring how people measure sharpness. So that's why I didn't say it explicitly. So I was hinting on that. Maybe the overall idea is I want to draw the links between all these ideas and utilize SAM to as an auxiliary measure. SAM, which is S, stands for sharpness here. So to show that it is actually one of the viable approach to measure robustness as well.
Okay, so you want to show a correlation between sharpness metrics and
yes,
robustness metrics.
Yes, or if there is none of those. So I want to just clearly answer whether the correlation exists or not.
Why do you think that they should be correlated?
Because in my understanding, flatter models are flatter because the average loss value within that, say there's an optimal model, or the weight that is basically, say there is an optimal minima, then the flatter model will be more robust to perturbations in the neighborhood around that minima. So that is in the line with adversarial perturbation. Adversarial perturbation is nudging that model to a very different prediction or very different loss value. So if that loss value does not change a lot, that is a good property that a robust model should display. So I would say intuitively, there is reason to believe that flatter models should be more robust, and we're yet to test the hypothesis in empirical evidence so far. So I would want to explore that direction to see whether these things could be explained in a comprehensive study to show that whether sharpness indicate robustness and adversarial robustness is that equivalent to a noise robustness, and also the three-way correlation between these three notions. Do they translate to each other or not? Or there's a misnotion or misnomer going on that these things, if our empirical result doesn't show that, I unfortunately that we might have to say that these three things do not really indicate each other. So that's the thing that I want to study or verify in the future.
Do you think if you find that negative result, that could inform like better understanding of like what is sharpness, or like what are these sharpness metrics actually measuring?
Yes, I would say as long as we look into the loss landscape, I don't think I mean, for example, if we only visualize them, it might not tell us the whole story, but if we try a set of different, say, sharpness metrics, for example, by measuring the largest eigenvalue of the weight matrices, that a lot of things share the same intuition of exploring what is the model that we train is actually doing. Or I think the current, like the current community, machine learning community, what we're lacking is a way to quantify certain property of the model. And I would say sharpness seems to be one of the most promising quantification that is currently there. And then yet there's not a whole lot understanding about it. So I would want to see if actually it deserves to be a best candidate there. So I want to do a work that is going along the same line of sharpness, and then to see whether it fits into the audio machine learning paradigm as well.
I have one more high level question.
Sure.
Well, it's sort of, you can choose to answer one and not both, but it's two questions that are sort of related. So what would you say is like the 1 to 2 key takeaways from like the work that you've done so far, or maybe the work that you intend to do as like the body of work that's your thesis? And so the two questions are, for like a general, like a machine learning practitioner right now, who's not necessarily a specialist in speech, in terms of research or adversarial robustness, but is doing like practical related machine learning research, or to someone in the future, who's working on machine learning once transformers and CNNs are like no longer what we use as models.
I'm sorry, let me rephrase the question. So it's like, in the future.
Take right now for someone who's working on machine learning, like an industry, and let's say in like 20 years, like I'm quite positive that we're like not really going to be using transformers or CNNs in 20 years, right? So like, what are the takeaways that people will have then?
Wow. So yeah, I think I have some philosophical answer to this, because this is a question regarding being time tested or not. And in my experience, the work that I think is novel at the time might not be robust to time testing in the long run. So what I found not very interesting, but a comprehensive understanding and then a detailed study tend to withstand the test of time better, in my experience. So I would say if we offer a suite of tests, as I proposed, to do everything in a fair and a square manner and show people what are going on, what is actually going on deep down in the bottom level of all these deep learning networks, then we might be able to have a clear notion of what is the best way to develop a model that is high performing. As I said in my talk, right? So we are seeing the field of perception is merging. Everyone, no matter what they propose, ConvNet or Transformer as a King Kong versus Godzilla, but they are actually stealing each other's technique in the latest form, where whether it be in ConvNextNet or Swing Transformer, as I said, like they are merging. So I would say, yes, I agree. In the future, or maybe 20 years down the line, nobody's gonna use these things. But I would say in the perspective of history, if we document all these changes and then trying to have a unified view to quantify what are, or specifically point out what are the property of each individual like characteristics of these module, I think in the future, when people look back, they will have a good benchmark to refer back to, and that will withstand the test of time. So I'm not trying to say,
Okay, what's the takeaway? Or if the takeaway doesn't, because you've already done a bunch of this benchmarking and a bunch of this work, right?
yes.
So what is the takeaway that they will have now? Or if it doesn't exist yet, what is what you're proposing? Like, how is what you're proposing going to provide that insight?
Yeah, I think I have another sort. Yeah, I think I can answer that question from more detailed perspective. So takeaway is that there is no model that is silver bullet to all right now, but we're seeing there might be in the future, because we are seeing the perception as merging. We've done all these studies on all these different models. No consensus yet, but the field is kind of converging to there might be an evident model, especially informed by the large language model, right? So the work that we have done, it seems like in the future there might be a kind of a universal architecture that can tackle all the tasks. And robustness wise, the message is here that it is still complicated, but with a proper measurement, I think the overall message is we should be aware of developing those metrics alongside of developing models. So the community can have a better sense of how or what is the best way to build a robust model in the current landscape, at least. So that's my two messages, because my questions were how to make them perform better and then more robust. I would say 10 years later, I don't think I will regret that my answer is like, as I mentioned before, as of now.
Okay, I'm done. Thanks.
Thank you. Those are very good questions.
Yeah, I can.
Shinji?
Sure. So what, thank you for your great talk. I have a lot of input in this 50 minutes. So, my question is first, so especially part one, you mostly working on the audio
Yes.
sound classification task,
Right.
right?
Yes.
So the first question is why you choose the sound classification task for this kind of a benchmarking?
Yeah, I would say general sounds are informative, just as informative as ImageNet in video, because I mean, I took speech recognition. I understand speech recognition as well, but the majority of this audio community, the current landscape is on speech, which I think is a little, it is a little too narrow in terms of a human sound perception in general. There are a lot of other sound except for speech that exist out there. So clear understanding of what model performs the best on general sound should inform speech model design as well, and not vice versa though. So I would say, instead of studying speech, I would say from a machine learning perspective, the environmental sound as we seen contains more variation and are more, say, like structurally interesting versus human speech. So it's a different set of problem that we're solving.
Sounds good. So mostly the finding here can be applied to the like a speech or music or other problems. So this is the reason that you kind of choose this task.
Because in audio set, we do contain speech and the music as well.
So the second question is still this line, but still classification is a little bit simple task, right?
Yes.
Do you have some comments about this direction? Again, you know, this work, the input is sequence, but many of the other the speech or audio tasks are actually more structured output forms. And then my question is that these kind of findings still universal, or these can be changed if we consider this kind of a structured output prediction problems?
Yeah, I would say that's a very valid and very good question. So I have thought about it many times. That's also what came up in self-supervised learning. So in self-supervised learning, we've actually seen that the sequence reconstruction task that can improve classification as well. So I don't think it's a black and white answer. The classification task itself might appear as easy, but doing it better and better using other things, other sources of information, we are not doing, I believe we're not doing trivial improvement to the overall system. Like, because there are constraints in sound, we lack overall labels by a lot versus speech community. We do not have a lot of label data set versus speech. We can just have someone sit in a room for hours and record the labels. In sound, nobody knows what the bird is speaking. I think we should a way to expand the current perception of sound, we can only leverage, or classification seems to be the most viable task that we can study first, but we are not constrained to only the classification specific architectures or methodologies only. So what I'm exploring is, as you can see here, we are exploring sequence modeling techniques in classification as well. And then that seems promising trend. So if we would be able to leverage sequence modeling techniques more in the future through self-supervision, I think we are able to address the unlabeled or lack of label in sound audio community better in the future. That's my hope or vision.
Okay. So yeah, still a similar direction there. Even in the sound problem, we have several structured output tasks, right? Audio event detection, audio captioning, or even sound separation and so on can also be a kind of categorized as the sound problems, right?
Right.
Have you ever applied these kind of discussions to such kind of other audio event tasks?
For audio event tasks, I think the
audio event detection, for example.
Yes, so for audio event detection, the problem is again the constraint of a data set or the existing labels. So for audio captioning, for example, I've shown that we know what we're doing in video to text retrieval. That's applying the same sort of a notion as an audio event detection. But in the audio set case, there is no like a public benchmark on audio text retrieval yet. And then the difficulty of setting up these data sets are a little more intricate than image to text pairs, because I believe the labeling cost of collecting a large set of labels for audios are more expensive than video, because it's just harder for the labelers or annotators to have a high quality annotation of a certain audio event, because they are not expert, and then it's hard to kind of bring them into a uniform standard to label these audio captions. The existing audio caption data set, as far as I know, are very small scale, and then they do not generalize very well. So in the large scale setting, this is a little bit of a, say, problematic to what I am seeing. That's why I would say exploring more on self-supervised learning through reconstruction, or even using a sort of a generative model to generate condition on certain class might be able to let us explore larger sets of audio data set in general by, for example, using diffusion models to generate more audio set-ish sound than we can train on a larger variation of a sound classification.
Okay. So, yeah, still part one. Among all the kind of your investigation, currently, what is the kind of best combination in terms of you showed architecture optimization,
Yes.
trick, data augmentation, etc., etc. What is the kind of current best combination in your experience and in the community?
Yes.
I'm just curious.
Cool. Yeah. So I think what we are showing on this slide is the best performing audio set model, which is the swing transformer setup with a masked autoencoder as a self-supervised pretext task. So this is the best combination. And in terms of optimization tricks, learning rate decay with step decay tend to be the best correlated with the linearly scaled batch size. And on top of that, all sorts of data in-domain data augmentation, including class balancing, mix-up, and then spec aug, which is audio specific augmentation, they all tend to help with the performance gain. So our current system have all those things built inside, and they, like the system we're showing here is at least showing 47% mean average precision, and that is the highest number we can see on audio only system so far on audio set.
Sounds good. So self-supervised model, swing transformer, and the learning decay.
Yes.
Cool. So the next question is the adversarial perturbation. You showed it's very interesting. You changed it to the for each higher frequency, lower frequency, or you also change it to the temporal, right?
Yes.
Can you tell me why the temporal is actually not so much?
Because yeah, we try to interpret what's going on. So the mask of a temporal, because we're designed as I think that goes along with Dan's question originally as well. The problem we're finding in temporal masking is that because of a weak label in audio set, the event might not fall within the same temporal domain of this X seconds, for example, within that 10 seconds. So moving along the temporal domain, the adversarial noise might or might not affect the actual model at all. So this is, or might not affect the actual data class at all. Because, for example, if the hammer sound only exists in 4 seconds or 6 seconds, if the adversarial perturbation is computed on 8 seconds, that is not really doing anything. So That's my hypothesis. I think that could explain what we're seeing here. That's why the temporal masking tend not to change that much over different temporal axis, but I could change my mind if there are better explanations.
Yeah, probably I think it's right, but again, I am more interested in the like structured prediction problems. Like if we change this problem to the audio event detection and so on, I guess the conclusion would be changed.
Yeah, we're yet to explore that. I think we can test this hypothesis on other audio tasks and then see whether the observation would change or not. But on classification, it doesn't matter. This also goes along the same line of how we compare different pooling functions. Different pooling functions do not affect the classification score that much, but they do affect the localization accuracy by a little bit.
So that might kind of overall my how to say question about your thesis. Some of your take-home message might be changing when we move to the other task.
Yeah, that's.
I see that the classification is the first approach, and also I see that it's a larger data, and it is also very how to say well-defined metric.
Yes.
So these three are quite critical. So your kind of investigation is quite informative to me. And then probably in addition to the multimodal direction, I am also again more interested in the structured the prediction problems. So I'm looking forward to your kind of investigation in this direction. Maybe not in the your entire thesis, but in your long research life, that to find some more universal the findings in the various audio event would be very kind of cool. So that is my kind of comment. Yeah.
Thank you.
Okay.
Yeah.
Thank you so much, Billy. Yeah. That's from me.
All right. Thank you, everyone. Given the time and the time that we've reserved, I'm going to hold questions for discussion later. I want to open it. I want to open it up to the room. If anybody has questions from on Zoom or in the room.
Slightly.
Sure.
It's maybe not the best question, but in reference.
Oh yeah, so that is the definition of a weak label. So because audio set is a weakly labeled versus strongly labeled, as I briefly mentioned here. So weak label means we do not know which second does the event actually happen. So we only know car exists in this 10 seconds, for example. So striding the temporal mask might not even cover the car sound actually. So that will result in a sort of a uniform penalty to all the classes that will result in a sort of a basically an average decrease of all the classes versus a specific targeted attack towards one specific class. That's my guess, or educated guess based on our observation.
All right. Any other questions? If not, then let's thank the speaker again. Thank Billy again for the presentation.
You're welcome. Thank you for coming. Thank you for your attention.
And maybe could I ask the non-committee members to leave the room at CMU
Yes.
including Billy.
I
And
the recording. Yes.
yes,